Yeah, fine. Okay. Excellent. So let's restart addressing our NoSQL sessions. For the time being, just to wrap up what we said yesterday, there were few slides, but there was a lot said. So what you have to bear in mind within all that has been said is the following. So the main characteristics of NoSQL stores. So they do not provide complex querying functionality, and the reason is because they prone to have simple data models, simple in terms of data structures. So if you have simple data structures, the kind of operations that you can perform on top of them are simple, and so you provide a simple querying functionality. Of course, if we get rid of the relational model, we do not no longer have the possibility of expressing queries in SQL. And they provide, on the other hand, crude operations, so create, read, update, and delete through specific APIs. Okay, so you have the data store that implements a specific data model, and then it provides you with the API with the set of operations that you can perform on top of it. And normally, these operations are CRUD operations. Since we say that we are preferring simple functionalities, well, there is no support of joins, okay? So some of them materialize simple joins, and they give up, well, okay, so some of them have implementations of simple algorithms in order to perform joins, or the initial operations such that a programmer can implement some join according to the requirements of an application. And then, of course, yesterday we discussed a lot about normalization. So there is no longer normalization. So the properties ensured by normalization are over. So you can have null values, you can have missing values, you can have repeated data, which means that for example, if you update, you have to go and track all the items that you want to update, okay? Because you are not longer sure about the unicity of the items provided by normalized schemata. So that's another important characteristic to remember. And then, with respect to the execution model, remember that DBMS in general has two models that guide its characteristics. The first one is a knowledge model that describes the data model, that is the set of structures that you can use in order to represent the data, and a set of operations adapted to these data structures in order to manipulate the data. That's the knowledge model. And then they have an execution model that describes the conditions and the guarantees, the non-functional guarantees that you can expect from the system with regards to the data management. And so the one that you have already studied is the relational solution, which means that, which is the basic data structure used by the relational model, the relation. Okay, so you have the notion of relation, and then the operations that can be associated in order to manipulate the data. And there you have at least two types of languages, the data definition language and then the data querying language, where you have specific operators that that help you query the data, the relational database. So that's an example of the knowledge model regarding relational systems. And then the execution model associated to these relational systems is the unit of execution is a transaction, and a transaction ensures ACID properties: atomicity, consistency, isolation, and durability. Okay, so these are the guarantees that any relational system provides. Okay, so if you change from store, so these guarantees can change. Normally in NoSQL systems, you do not longer have all the transactional guarantees. And you have partial guarantees. We will go into details today, I hope, and then, but anyway, the execution model change. And some of most advanced stores, what they provide you is with a set of fine-grained properties that you can tune according to your requirements. Example of this is, for example, atomicity. I don't know if you are aware of this, but for example, atomicity, there are several models that can implement atomicity. The one that is implemented in relational systems is strict atomicity, so all or nothing, but there are other relaxed versions of atomicity. So some systems let you tune the level of atomicity that you require. In fact, today's relational DBMS let you do that. Okay, so you can play with the properties, but these are the modern relational systems. In classic terms, I suppose that these are those that you learn in your courses. There's no possibility of tuning anything. The idea is that you ensure the different properties. And for example, in the case of atomicity, it's all or nothing, so a strict atomicity model. And all these three groups of characteristics that you have to bear in mind seek for the same objective, which is achieve high scalability. Okay, so that's everything that is done in terms of simplification of the knowledge model, simplification both of the data structures and the operations, the execution model, and the way you tune your execution model are directed and are oriented to seeking for high availability. So that's the objective. Now, since we have these two elements, so let's have a look of the possibilities of the different families that you can have if we think only about the knowledge model. So first of all, the data models. So the different families of data models provided by NoSQL systems rely in three basic data structures. The first one is the most simple one, is the notion of tuple. Okay, a tuple is a set of attributes, attribute value pairs. That's and then the values are typed, and a type can be simple, well, can be atomic, or can be complex. So in the general definition of tuple, you allow attributes to be type structure, okay, of type tuple. So it's a recursive specification. So, and within this definition, you can find again the relational model, okay? Well, in fact, partial representation of the relational model, which is the tabular notion, okay? Not the with the associated integrity constraints. So it's just the data structure. Then you can have documents in terms of data structures that can have lists or of scalar values, and that do not have a specific global schema. Example of this is any XML document, or a JSON document is an example of an item that belongs to the document data model. And then you can have extensible records where you have, again, tuples, but tuples for tuples, etc., and that give you the possibility of having more complex data structure. So it's a hybrid between tuple and document. And in all these cases, since there are no integrity constraints, you can accept some items of a data set having a specific structure, and other elements of a data set having a variation of an initial structure, and all these items can belong to the same data collection. Okay, whereas in relational, you can't. Other relations have the same schema. And out of these three general data structures, you can have families of data stores. Today, you can find in the market 5 families of data structures. Those that adopt the model known as key value, where you have the representation, the abstract name of a value, and then a value. Okay, so in a very simple manner. Okay, so it's example of this is, for example, the images that we store in our computer. The key is the name of the file, and the value is the blob. Okay, that represents the image. So that's an example of a key value data collection. Your music, you have the logic name or the identifier of a song, and then the content, well, again, the blob that represents the song. So that's a key value data example. And then you have documents, for example, the set of HTML pages that compose a site, yeah, or XML files or JSON files. That's document stores, so those that are able to deal with these data structures. Then there are extensible records. Extensible records is, imagine an Excel file, but where every attribute of every column of the Excel has a history. So you have every column has another dimension. Okay, so you have the versions of the values, for example, that are associated to an attribute. Example of this, imagine that I want to deal with the I have a document, and I would like to have the different versions of the document. So I have the document, I do modifications, and I have a new version, and then more modifications, and I have a new version, and I store all these versions in a column. That would be an extensible record. And so you can reason also in terms of the columns. So you can have more or less columns that are connected within each other. So it's like having linked list of columns, but where the columns themselves have another linked list representing the history of the values. So these are extensible records. Then the other family is the family of graph stores. Um, some years ago, graphs were very interesting data structures for dealing with experimental sciences. For example, for representing DNA in biology, for representing astronomic entities in astronomical databases. So the graphs were quite useful in order to deal with this type of data. And then social networks emerge, and we have a boom of graphs. And well, the set of connections that you have in your preferred social network can be represented as a graph and can be stored and manipulated, etc. And so there are stores that deal with this type of data structures. And then, of course, there is the relational data stores with all the characteristics that you know, and I will not repeat here. So just to give you an overview of the characteristics of every family, we will, I'm not sure if today or next time or during the week as a homework, we will touch a concrete example of this, but I would like to give you, the general characteristics of these different families. So key value stores. What is I'm going back to the characteristics. Okay, so I have the data model, which is key value. Then how do I organize these key values in a storage model? Okay, well, I can use, for example, hash tables in order to organize all these key values, sets of key values that compose my database. Okay, so the index that I can use in order to organize and store a data collection of this type would be hash tables. Then if I want, and why? Again, because I need to scale. You have guessed, this is something that we learned at the beginning of our studies. Normally we need indexes in order to organize the information, because we, at the end, we very often, almost always seek for performance, okay? So, and then what are the operations where I can create a key value element? I can read an element giving the key. I retrieve the value. I can update an
Teacher,
element,
excuse
and
me.
a key I provide with the new value that should be associated to this key. And then I can, for example, delete an element from a data collection. So I give the key, and then the associated value will be deleted. There are many, well, this is the most simple way of managing data. If you have a course on storage or in data structures, I'm sure that some of the exercises were like this. Okay, so the only difference is that in those courses you are asked to program all these, and when you have a key value store, this is delegated to the store that provides you with the right data model, that provides you with an automatic or more or less automatic way of creating the hash tables in order to organize the data on top of a set of hard disks. And then, of
Excuse
course,
me, doctor.
provides you with the API. Tell me.
I have a question. Could a dictionary be a key value store?
Yes, a dictionary. Yes, a dictionary is a key value. Well, can be modeled as a key
Yeah.
value store.
o-
Exactly.
Okay. So it's like a model where you use hash tables in order to store all the data.
Well, you have key value. So your
Okay.
example of dictionary is right. You have the word and then the definition of the word, okay, or something associated to that word. Okay, so that's first thing, and then you can have like that many items, and then since you are looking for high performance, you have to index this collection in some way, and the right index structure in order to organize this is a hash table. And I think that this is the only one that you can have. Okay, but the index is just because you want to go fast. Otherwise, well, this prevents you from looking item by item. For example, if you have a read operation or a delete or an update operation.
Oh, okay, I see. Thank you, teacher.
Mhm. Okay, so as we said, that is not a declarative language. So if you want to explore and query such kind of database, well, you use these operations within a program, and so you and you manipulate it. Okay, so in C or in Scala or in Go, okay, or any other language. Examples of these, well, you will see that along the examples that I have provided, well, they are the major examples of commercial data stores. You will see that most of them are provided by very important companies. For example, Redis was one of the first tries with key value stores, and it was provided by Google. Scalar is two. SourceForge provided a key value store called Tokyo. Voldemort is a very well-known project that is, it was a startup at some point when these kind of data stores emerged. Raya too. Then there are others. Well, if you have some uh, algorithmic course, advanced algorithmic course, you might be acquainted with a technique in order to organize data in memory, which is called membase. And so this comes from the distributed systems domain. And at some point, there were people that said, okay, we already know how to deal with this kind of data structure. So let's implement this model within a data store. And so they apply the membase, well-known distributed systems algorithm as the core of such store. And then, well, there's membrane too. I think that membrane doesn't exist anymore, or it didn't uh, well, went to the top preferred key value stores in the market, but it was an important one at some point. Okay, so this is, as I said at the beginning of the course, this is really going back to what you already know in data structures. But in this case, you have a system that uses this approach in order to provide a data management solution. Okay. Now, examples. DynamoDB is an important one today. It is provided by Amazon as a service. And so it has, then of course you have the generic model, and then in the implementation, well, different vendors implement the model in different manners. Okay, so in the case of DynamoDB, keys are unique identifiers. Of course, knowing how to identify, well, how to build the key uh, should be associated to a naming model. I suppose that you know this from algorithms or in operating systems. In those in those courses, we usually learn this, is that the naming strategy to be adopted in a computing system is, in general, is either implicit because well, the administrators or whoever manages the system have already decided about this, or it is up to us to give the rules in order to provide with data with identifiers. And then we can decide whether these identifiers are unique or not. If the naming system ensures that it will generate unique identifiers. Okay. And then then that's the kind of reasoning that someone should have when using this or designing this kind of solutions. And if you are users of such a solution, you have to go and within the characteristics that in order to understand what the system provides, you should go and see which are the strategies adopted in order to define unique keys, well, the keys, if whether they are unique or not. And then with respect to the value, it's how big can the value can be. Okay, so a value in the case of Dynamo in the classic delivery is less than 1 megabyte. Okay. Then it provides with only two simple queries, put and get. And this is something that you know because you have programmed on the web. Okay, so these are the two operations that it provides. And then well, that's too simple, but not that simple, because I have insisted, maybe not enough, but I have said that in order to go fast, in general, these stores try to put as much as possible data in main memory. Okay, and yesterday we said, okay, that's great because you can go fast, but then there is a problem of durability because main memory is volatile. In order to address this problem, they work with duplication. Okay, normally these data stores, we discussed this yesterday, run on top of clusters. Okay, this is why, for example, in the content of the course, the topic is cluster-based data management solutions. Okay, because they have been designed in order to work in clusters. And when you have clusters, you have different machines. Since you are scaling out, you have different machines, complete machines with their own main memory. So in order to solve the problem of durability in main memory, what they do is they duplicate data across the different nodes of the cluster, and therefore see if one some data goes out in some main memory in one node, then you still have the copies in the other nodes. So they copy this data, but the problem when you copy data, when you replicate, is that if data is modified, you have to make sure that all the copies are modified too. And this is called convergence. Okay, so what it provides is it ensures durability through data duplication across the cluster nodes, and it gives mechanisms that will make sure that all the copies converge at some point. There are other aspects that, for example, in relational databases are ensured per se, which is, for example, security. In the case of NoSQL stores, security is not, should not take security for granted. Okay, so in the case of Dynamo, they rely on the security system of the cloud. In the case of Amazon, well, the security solution is quite reliable. And so thanks to this, thanks to the environment, thanks to the cloud, then security is ensured for the store. Otherwise, again, if some application or some organization using Dynamo is willing to have a more developed security process, for example, out of the cloud, I don't know if, well, I haven't told you, I don't know if you are aware of this. You have the cloud, and there are other servers and other machines that are connected to the cloud, but that do not belong to the cloud. And this is called the, well, the edge, okay? And in fact, you have the edge and you have the fog, okay? So there is a set of elements and servers running out of the cloud that compose a fog that is connected to the cloud, okay? So normally, well, if there are servers, you call it in fact the edge, and then, for example, if you have other sensors and other computing devices with computing capacities that are in the nature, they are called the fog. Okay, so all these elements that are connected to the cloud are give security issues, okay? So what Dynamo says is, as long as your operations remain within the cloud, they are done in a secure manner. Everything that is done out of the cloud, for example, if you have applications running on the fog or on the edge, but that connect to Dynamo, if there you have to implement security strategies, okay? Because this is out of the context of the cloud. What it ensures also is high availability, scalability, and performance. And it executes the operations under a parallel programming model called MapReduce that we will study in the course later on. But anyway, what it says is that beyond the fact that I have a lot of computing resources, I also implement my operations in a parallel manner, and you can yourself program the operations that you want to associate to your database in parallel, and the system will make sure that the execution of these parallel operations is done correctly and in a more or less transparent manner. Okay, so it is as if you do select star from employee, and the system behind runs this selection operation in parallel, okay? But you do not care. It's hidden, the complexity of parallel execution is hidden from you as programmers, okay? As people defining, for example, a query. So in the case of Dynamo, you put some gets and maybe other operations, and they are done in parallel. How those, well, they call them tables because a key value is a form of table, okay? And let's have a look at the characteristics. For example, here we deal with users, and so we have users IDs, which are strings, okay? And we decide that these strings will represent the identifiers of the value, okay, of an associated value. And in the case of this database, the value is a tuple of 4 elements: the name, the surname, an email, and age. But as you can see, these attributes are not mandatory for all the items stored in the database. Some have an element age and an element age like this one, but others don't. Some have an associated email, and others don't. And all of them have name and surname, but some of them could have a surname and not a name, or the contrary. Okay, or they could not have name and surname and only have email, and that's it. Okay, so this variability of the genetic data structure is allowed within the items. And so, as we said, the only guarantee that the only constraint that that the Dynamo imposes is that the user ID must be unique. So I cannot have two Joes, or then I will have Joe 1 and Joe 2, but never the same string. Okay, because it should be unique. Otherwise, here you can do whatever you want. And then, well, we can have, what are the type of things that we can do? For example, we can have lookup questions, get John 85 information. So John 85's name is John, the surname is Williams, he has an address, a Gmail address, and he's 17 years old. I can get the mail of a user ID called Anonymous. Anonymous, the email is no name at gmail.com. Okay, so these are the type of questions that I can perform. And then if I am willing to execute more complex ones, for example, which is the average age of the people stored in this database. So in that case, I have to program this. Okay, what would I do? Well, I would go through the different items of the database, asking for the age, and I would have a dummy variable where I store. I do the summation of the ages, and since I can know the number of items, well, the number of times I found an item, then I divide it out of the number of items, and then I have the average age. No? And this is a sequential way of programming the query. And then behind, I could have, instead of programming it sequentially, I could program it in parallel. Okay, and then having, for example, all the ages, and then and then doing the summation of subsets of my items. And once I have done this, I compute the average. Okay, so then I divide it by the number of the items, and then I can have a very simple parallelized version of this program. But anyway, this should be done by a human. Questions until here? So as I said, it's like data structures and algorithms at the beginning of the studies, nothing more. Right. Okay, so let's go to document stores. Documents are much more complex data structures. They are in fact they're a version of key value stores, but where you have a key, so you have an identifier, but instead of having any value here without any structure, explicit structure, predetermined structure, here you have, for example, an XML, a JSON, an HTML document. So this means that data stored, in fact, deal with semi-structured documents. I think that in advanced databases, you studied semi-structured data models. And otherwise, if you haven't, you know what is JSON or XML. So these are semi-structured data models. Well, a particular aspect is that you do not document stores do not impose you to predefine the structure of your documents. And then, well, the operations, the API is a little bit more complex than the key value stores. You can insert a document, giving the key of the document and then the document. You can fetch a document out of the key. You can update a document by giving identified by a key, and then you can delete a document identified by a key. And then here, depending on the implementation of the store, you can accept to have one version of the document or several versions of the document, meaning that a document is created, it's transformed, but it's never deleted. Okay, so you keep all the versions of your document. For example, a system like Couch TV does this. So you create your document and it's version 1, and then you operate on it, and every time you operate on it, it creates a version, and then you can access the versions of a given document. Okay, a classic example of this solution in systems that we use, if you are acquainted in using Google Docs or any Office document in OneDrive, you might know that it keeps the history of your documents. And if you, for some reason, delete something or do an unglorious operation on the current version of the document, you can go through the history of the document and then retrieve a previous version. So this is the principle of dealing with this type of solution. So that's something that we are quite used to do, but that maybe we're not aware of the power of and the interest of this. So this is because behind there is a document store playing with this. So as I said, one of the most popular ones is Couch, and maybe the most popular one is MongoDB. That's the one that we are going to use. There is also SimpleDB by Amazon, and TerraStore is also very well known, and it is a system by Google. Okay, so you have these different solutions. And as I said, we are going to have a look to MongoDB in order to have the full experience of dealing with document stores. So normally many of them, and for example Mongo, but also Couch, use, in fact, adopt as internal data model JSON. Okay, so I remind you that JSON is a kind of semi-structured data model where you have tuples consisting of identifiers of the elements and either simple or atomic or complex elements. So for example, here I have orders that is composed by a simple attribute called date with a string here, and then it has another attribute which is a complex attribute, which is a list of tuples where the tuples contain three attributes: product, quality, and subtotal. Okay, and then you have the associated values. Everything is a string, and then it is up to the system in order to, if there are scalar elements, to convert them to scalar. And in some solutions, you can have a kind of schema that looks like this. This is for JSON, okay? I'm not talking about any store, I'm just talking about JSON. So some solutions try to extract the schema of the documents that look like this. For example, here you can have a description, etc. Okay, but anyway, in the Sauvage way of dealing with JSONs, Stores do not assume anything about the structure, they accept it as such. And as I said, they do not respect the first normal form, so they accept data structures as values of the different attributes. Now, I insist a lot, well, here we are in the theory course, and it is very important that you learn to use a professional vocabulary of computing science. This shows that you went to the university and not that you went to some school for learning just technique. Okay. So the main difference is to be able to associate theory to implementation and to know that implementation always makes hypotheses with respect to theory. Theory is the ideal way of how we can do things, and then because of many reasons the implementation is just a version, a close or less or far from theory, and you have to always be aware of this and be able to name things as correctly as they should. Okay, and then accidentally vendors and community and whoever you want talk in a very colloquial manner. It's like being a, um, a physician. You know, physicians, when they have patients, they talk to them in a colloquial manner, but in order to interact with other physicians and reason about health, etc., they have their own vocabulary. Well, the same should be in our case. We have our professional vocabulary out of our discipline, and then we are of course able to use a colloquial vocabulary in order to interact with vendors, with other people, with users, with people from other sciences. But we always have our vocabulary. And so this is why I insist a lot. This data model doesn't respect the first normal form. So that's something that any person going to the university should master, first normal form, normal. Okay, otherwise, no need to come to the university. Okay, so let's go to much more complex data structures. As you see, it's like if we were going through a spectrum. We are starting with key value data structure, a very simple one, but still we can provide interesting data management solutions for this. And then it becomes much more complex, and you have document elements. And now it's becoming quite much more complex. You have tabular representations, but where you reason not about the table as a unit, but the unit of reasoning is a column. And so you are going to navigate through columns in a horizontal and in a vertical manner, and then in 3D, in fact, because as I explained, all the columns have histories of values. Okay, so it's like now we have a 3D space, and we go through the columns, we go through the values, and we go through the histories. So there are many different implementations of column stores of this kind of, they are called extended records in the data structures jargon. There is one very popular, which is not here, but it should have been. It's Bigtable. Okay, Bigtable is by Google, and it's a very, very popular NoSQL store. Okay, so what are you going to do? Well, it provides any columnar database will provide with the necessary operations in order to navigate through this complex multidimensional data structure. So you will have looking by key, looking by column, looking by history, this kind of operations. If we go back to theory, well, it is a denormalized tabular representation. And there is no fixed, it's not diagram, there is no fixed schema for the columns. Okay, so it's like relaxing the relational model and decomposing the tables in order to be able to compose our tables by combining columns. Okay, this is the principle. Oh yes, here it is. There is Apache HBase, which is a very popular solution. Cassandra by Facebook is also very popular. There are others like Google BigTables, Druid. So many solutions. They are quite interesting when dealing with analytics. I'm not sure whether in your advanced databases course you went through data warehouses. Have you touched this topic? Multidimensional data models?
Yes, we have seen that warehouses.
Okay, so in data warehouses, particularly in the multidimensional data model, you learned a lot, no? So there's the idea of this hypercube. Normally, we think in 3 dimensions because these are the ones that normal humans deal with. So you have this, let's say, a 3-dimensional representation, and then you could drill down the cube or extract pieces of the cube of this multidimensional representation. So there is a relational solution for this, but it is challenging to ensure performance when the cubes become very complex, okay? And expressing queries in SQL with this with a relational solution can become very complex. And so alternatives to these solutions are these big tables. So they are well defined in order to aggregate data represented in multidimensional spaces and then analyze such data. Okay, so this is the NoSQL solution for implementing data warehouses. And also with the possibility, this is not said in the slide, but the possibility is that many of these solutions let you program in parallel. Okay, so you have the right data structure in order to think about multidimensional data, and then the operations are parallelized, so high performance is ensured in such manner. So it looks like that. That's a nicer picture of what I have been drawing in the air with my hands. Here is an example. I will not go through it because having the reasoning about multidimensional solutions would be a course in itself. So I have to decide how to prune the content. But anyway, normally for example, in Cassandra, what you have is a notion of columns, which are tuples of key value and timestamp, because you are dealing with histories. Okay, so all your data is timestamped. Then you can have families of columns, which are containers of set of columns, more or less the notion of table, again with the idea that it's up to the application or to the designer to group a set of columns into a column family in order to represent something, but the columns, you can reason about columns in an independent manner, which is not the case in relational. And then you can have super columns, which are lists of columns, okay? So in that way, you can here you can be close to the notion of view. Okay, so I have my columns, I have my families, and then I can have lists of columns or families composing some representation of the data that I need to provide to feed the requirements of some application. And well, this is the case. The course in the program has been organized as if it was like you have fundamentals of databases. This is fundamentals of cloud computing and big data. Okay, I'm just giving like pointers, and then I decided to prune, for example, these analytics. Again, there are many solutions, and then you can reason about many different aspects in order to deal with this type of analytics. So I will not, I prefer not going into this, and then provide you with like the spectrum of solutions, and then eventually if you decide to dig into some specific aspect, then you can have a tutorial or things like that. Sorry. Yes. So, well, I'm not selling Cassandra at all, even if it's, I find it a very interesting solution. But, well, another thing is that many of these stores are open source. So if companies are not happy or feel that there are some limitations with respect to what is provided in the normal delivery of such a data store, then since they are open source, there can be communities that specialize the solutions to deal with some specific problems. Or people in academia, if you are a database researcher, then and you are inventing the next optimization support for multidimensional databases, so you can, instead of programming a store from zero, you can have your open source version and then extend it in order to validate some idea that you might have. And then there are people even, well, coming from academia that suddenly realize that the solution, the specialized solution, is very interesting, and then you can have a startup just dealing with the cartridge that you developed. Okay, so there's also professional and economic industrial market out of such kind of exercise. Again, in order to ensure high availability, almost everyone does this. It implements replication strategies. And then here you are really talking about high scalability. Okay, we're talking about Facebook. Okay, so it goes beyond clusters. In fact, you can think about data centers where you have, on top of which you have Cassandra, and you can make decisions of the data centers, the pieces or the zones of data centers that you will use in order to deal with your data, your replication, etc. Okay, so there is really this notion of high scale in terms of reasoning in much more than clusters in data centers. Then another important thing is fault tolerance. The relational solutions, one of their very nice properties is that they are fault tolerant. If you remember from your fundamental database course, a relational system is one fault tolerant, which means that in the presence of a physical fault, the system will be able to recover. Okay, and there is also some contract, some guarantee associated to it. It says that it will the recovery process will not take more than X minutes, and It ensures, of course, the property of durability, which means that all the transactions that have been validated before the fault will be there. Okay, so you retrieve the state of your data, the right state, just before the fault. Okay, so but anyway, it's one fault tolerant. In the case of, well, today, the solutions that, for example, the bureaucratic solutions provided by OneDrive or by Google, they're more or less the same. Okay, so if there is a problem, a connection problem, etc., before the connection, they ensure you that you didn't lose your data, and this is why it is very interesting to work on top of this cloud solution instead of working locally. Okay, nobody works locally today. Then there is the notion of adaptable consistency. So adaptable consistency. So you want 1, 2, or 3 copies consistency. You can have quorum protocols in order to validate your consistency, and you can decide whether you need consistency for all the copies at the same time, or some of the copies and then eventual consistency for the rest of the copies. So there's a lot of tuning that is provided by Cassandra. Of course, this is advanced use of such a solution. Okay, it's like if you think about the relational database, well, if you are the administrator of a relational solution, you will have to do more or less the same. Where are you going to deploy the different servers that will compose your relational solution, which are the indexes that you are going to run in order to the queries that normally are run on top of the database, that they can run correctly. So, you know, this administration operations that are normally done in relational solutions, they are also here. Okay, this is not new for with respect to relational solutions. Any data management solution can should have an associated reasoning, tuning reasoning, in order that it works correctly. Well, Cassandra is based on Dynamo and on Google Big Tables, okay, in order to deal with the data model. So they adopt the model implemented by Big Table, the columnar model, as the internal model of Cassandra. Okay. So that's the kind of thing that. Now, what if we are not studying Cassandra? Why am I talking with you with this? Because what you have to keep in mind is these kind of properties. Okay, what are the non-functional properties that these data stores provide? Okay, and that any data management solution provides. Okay, this is the question that you have to bear in mind when you want to decide which data management solution you are going to adopt for a given problem. Okay, the non-functional aspects regarding distribution, centralization or decentralization of the operations, elasticity, availability, fault tolerance. Okay, and then if you are acquainted with the different strategies known today in order to deal with these aspects, you can go a step forward and say which is the strategy implemented by this system for addressing, for example, fault tolerance or high availability. And according to the adopted strategy, you can infer the way the system will work. Okay, without having to go and test the system. If they adopt a specific strategy, you know which are the limits of the strategy, and then they will not go beyond this. Okay. And this is what, again, makes the difference between going to the university and not going to the university. In the university, we study the strategies, okay, the characteristics of the strategies, the different protocols, we are able to compare them, such that when we go out in the nature and we have to face these systems, we have the strategies in mind, and nobody can tell us that they go beyond something because we know the limitations of such strategies. Okay, so this is column stores. And now, okay, so we're happy, we have different models and we have solutions and strategies and blah, blah. Okay, but how do they really work? And which is the kind of difference that that we can see in the way we are going to use such a solution. There are some people that start using NoSQL, any NoSQL solution, and they say, you know, it runs very slowly. They are promising high performance, and this thing runs like it takes ages in order to deal with the data. And this is because the system is tuning, okay? And we have to go back to the design and construction process of a database that we find in these NoSQL solutions. So what happens is the following. We have data as the ones we described in the introduction, raw data with bloodly formats, etc. And there will always be an ETL process. Remember, ETL means extraction, transformation, and loading. Okay, so ETL is a problem by itself that we have to solve in one way or another. And anyway, at some point, we feed the data into a data management solution. And what we are doing, in fact, is we are populating the database. Here, which is the difference between what you know and these solutions, where in order to feed and populate a database in the relational solution, here you should have spent time designing the relational schema, such that when you load the data, you transform it into the specification of the schema, and then the database is populated. That's something that you know. I'm sure that you have projects dealing with relational databases. In the contrast, here there is no transformation to do, and there is no schema to define. You get the data, you prepare it, blah, blah, okay, a set of images, documents, etc., and paf, you populate a database. And okay, you're happy, it is there, and then you start querying. You try to explore. Okay, I have a set of documents, so what can I do with them? Well, I'm going to explore them, and so I'm going to go and see. For example, let's think that we have a set of documents describing restaurants. Well, I'm going to go and see which are the restaurants located near to Lyon and to downtown, for example, things like that. And at the beginning, since you have the bunch of data here and they have not been indexed in any way, so you have the bunch of data, queries will be very, very, what is the contrast of fast, slow, sorry, and so they will go slow. But what is important is that the system will start creating indexes according to the queries that you start performing. Okay, so as the more you query the database, the better data are indexed and the faster your queries start to be executed. Okay, so you really start from raw things, you perform the operations, and then the system starts to organize itself. Which are the decisions that it makes? Well, it makes the decisions on how to distribute the data into the different nodes of the cluster it is deployed on. How much it should replicate the data, and it also tries to balance the charge of the nodes that are participating in the management of this data solution. Okay, so it starts tuning all this. and putting data back and forth, etc. And then once this organization is done, then it decides to, well, in fact, it decides two things. Which are the data that are going to reside in memory? And how will the data be replicated across the cluster? And for each node of the cluster, there will be an indexing process. Okay, so quite complex things going on behind the back end of the system that will start tuning it and increasing performance. Okay, so now we are almost done, but it's good that I do not zoom in into the matter. So there are two strategies to be acquainted to in terms of this process. First, the strategies adopted in order to organize main memory, data within main memory. And as I said, many of the systems adopt well-known strategies that we knew from ages ago in the distributed systems domain. Many of them are a very important system and solution that has been again proposed ages ago is memcache. Okay, so normally many solutions, commercial solutions, adopt this memcache strategy that we will study next time in order to organize data in memory. And then replication, well, replication, we will touch some aspects of it because again, it's a problem in itself. And another thing that changes with respect to classical solutions, in fact, the relational solutions adopt a strategy that all the data must be stored on disk. Okay, and this is very interesting because this ensures durability, but it's very costly. And so these systems adopt a non-demand storage strategy, which means that the program should say explicitly to store some data in the disk. Otherwise, it will be kept in memory. Okay, so when do we decide that data should be stored? Again, this is guided by strategies that we adopt that refer to the type of problems that we want to address. And so again, what I will do in the next session is give you an overview of these strategies, because as I said, this is the difference between just doing technically and having a look at some in a professional and academic way studying these systems. So before we wrap the session, so 4 things to consider in this design and construction process. Data reside in RAM, and normally based on memcached strategies. Data are replicated and they are eventually stored. Querying means designing the database, and means also what about the execution model, where the execution model will be a programming oriented model, and normally they adopt this famous MapReduce, which is the parallel model that we will study when we will deal with big data analytics. And then many of the data management basic operations will be done on demand by the program, explicitly asking to do things. And what is very interesting from this is that remember that we are in a scale out setting, which means that the system, as the architecture is configured, the system will configure itself. So it's a plastic system. Okay, so if there are more nodes, it will organize the data across all these nodes, and if nodes are reduced or some node is not available for some reason, it reconfigures itself according to the resources that are available, and this is very interesting to see. We will have a practical experience on this, and we will be able to see this plasticity of the system. I think that for those that like at computing science, this is a great thing to see run. Okay, so we are going to stop here. Just some administrative announcements. We will start working on a first case. Okay, if you remember well, the way we are going to grade the course will be out of cases, study cases that you have to work on and develop. So I'm going to start proposing a first case study associated to NoSQL and also two readings. Okay, so stay tuned. I'm going to send this information so that you can, in background, start working on these aspects, and again, making sure that you are getting important things and you build them in your minds and you can apply them to concrete cases. So this is what will happen in the back end of the course, and otherwise, for those that are connected in the lab, I'll see you in the lab on Tuesday. And if you have questions, please, it's the moment. And if you don't, then you can leave.
Thank you, Doctor. Have a nice day.
Thank you,
Have
Doctor.
a nice weekend. Yes, have a nice Saturday and Sunday.
You too, Doctor. Thank you.
Thank you.